Good afternoon and welcome to hand-wavy chemistry. Alkenes, molecules that contain a carbon-carbon double bond, are able to exhibit isomerism due to their inability to rotate about that bond. And for many applications, a change in stereochemistry results in a change in chemical properties. This is particularly important in biological systems, where an enzyme's lock and key active site selectivity means that when we change stereochemistry, often the molecule becomes biologically inert, or even worse, it has deleterious effects. When we're first learning about how to synthesize alkenes, one of the methods shown is an elimination reaction. But there's a problem. Simple elimination reactions are not selective. Let's consider the case of butan-2-ol reacting with hot, concentrated sulfuric acid. This reaction gives three products: E-butyene, Z-butyene, and a little bit of but-1ene. And if you only wanted one of these products, you would now have to spend time and resources performing purification steps. So what's the alternative? One option is to not give the molecule any choice about where the double bond will form. For example, 2-methylpropan-2-ol. It doesn't matter which proton we remove with the hydroxy group, we're still going to end up with 2-methylpropene. Alternatively, we could use a sterically constrained ring system. For example, 1-methylcyclohexanol. It has to form the Z isomer. There's no alternative. And the ring doesn't already have to be there before we do the reaction. We could also have it come about as part of an intramolecular reaction. For example, an intramolecular aldol condensation. And as long as we keep the ring formed small, so 5 or 6 members, there's only going to be one possible outcome for the stereochemistry. And this isn't the only type of intramolecular reaction we could have. We could also have an intramolecular Wittig reaction. And because intramolecular reactions are typically faster than intermolecular, we don't really have to worry about dimers and trimers forming. And speaking of the Wittig reaction, that is actually a stereoselective process even when performed intermolecularly. We don't have to rely on ring strain. And whether we get the E or the Z isomer depends on the nature of the ylid. For an ylid, where we just have hydrocarbons or other non-electron withdrawing groups attached, we find that the stereochemistry of the product is primarily Z. Meanwhile, if we have an electron withdrawing group, something that can help stabilize our ylid, for example, a carbonyl, now we find that our product is primarily the E isomer. The exact reason for this stereoselectivity is still being investigated, but most likely comes down to the stability of the transition state when the ylid and the carbonyl come together. It is believed that they approach each other at a 90-degree angle, so they're offset. And if we were to arrange them in such a way that we kept the bulky groups away from each other, then we would expect the thermodynamically less favored Z isomer to form. But now, if we use a stabilized ylid, the reaction rate becomes much slower, and this transition state becomes a reversible step, meaning that given enough time, we should expect to see the thermodynamically favored product, the E isomer, being formed in preference to the kinetic product, the Z isomer. And this whole situation is a great example of kinetic versus thermodynamic control. Having an irreversible step gives primarily the kinetic product, but having a reversible process, we expect the thermodynamic product. But what are some other options for the stereoselective synthesis of an alkene? We started this video by talking about a general elimination reaction and saying it wasn't specific. But that's not always the case. For example, an E2 elimination reaction for an alkyl bromide can be stereospecific. We know from experimentation that the proton and the bromine need to be opposite each other. So if we start with a specific diastereomer, we should expect a specific alkene to form. Alternatively, rather than trying to make our alkenes by removing atoms, we could form them by adding some. For example, we could start with an alkyne, and if we reduce it by using Lindlar's catalyst, we end up with the Z isomer forming. And this is because before the alkyne can be reduced, it needs to adsorb onto the surface of the catalyst, as explained in this video here. But what if we want the E isomer instead? Well, in that case, we could use sodium dissolved in liquid ammonia. The sodium deposits its lone valence electron into the pi star orbital of our triple bond, breaking it, giving us a double bond, a radical, and a carbanion. This carbanion will then go and grab a proton. Another sodium can now come along and deposit its valence electron to pair up our radical, generating a new carbanion, which in turn will go and grab another proton. And just like that, we have an alkene. And because this process is stepwise and the molecule has some choice in how it's going to break its bonds, we end up with the thermodynamically preferred E isomer. Another stereoselective process that involves alkynes actually starts with a molecule that has two alkyne groups in it, buta-1,3-diene, sometimes known as diacetylene. The base catalyzed addition of methanol to this molecule results in the formation of an intermediate that is stabilized through resonance. And eventually, when we're going to add our proton and generate our alkene, it attacks on the side opposite the methoxy group, generating the Z isomer. So far, we have only focused on the isomers that form during alkene synthesis. Another class of reaction that can generate isomers are electrocyclic reactions, and these form a ring. And when they do so, the substituents can either be cis, that is on the same side of the ring, or trans, on opposite sides of the ring. But that is a story that I've already covered in this video up here. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.